Hello everybody. So in this video we're going to continue with chapter 2, functions, with topic 2.3, inverse functions. So we're going to start by talking about pairs of inverse functions. So let's take for instance f of x is equal to x cubed. What would be an inverse function? Let's call it g of x. What would be the inverse function of this? What's the inverse of cubing a number? Well, isn't it calculating the cubic root? And it is, right? These two functions are the inverse of each other. How do we know that? Well, let's take f of x equals x cubed. If you have the number 3, 3 cubed is 27. If you have the number 2 as x, and you cube that, you're going to get 8. If you have 1 and you cube 1, you get 1. If you have negative 1 and you cube it, you get negative 1. Negative 2 gives you negative 8. And negative 3 gives you negative 27. Now, if we go the other way in the other direction, and we use g of x, which is cubic root of x, the opposite would happen, right? Because the cubic root of negative 27 is negative 3. The cubic root of negative 8 is negative 2, and so forth. So the point is that when you have a pair of functions that are the inverse of each other, this is what happens. For f of x, let's say f of x is equal to x cubed. Then the list of numbers or values that are the domain, also known as input, the input values would be the domain of f, like these numbers we have here, right? To the left, 3, 2, 1, negative 1, negative 2, negative 3. Once we plug those numbers into the function, which is x cubed, we get the result, which are the y values, also known as the output. And that is known as the range, right? The range is the output values of the function. So we said that when we cubed 3, 2, 1, negative 1, and so forth, we would get these values here. So this is the output or the range of x cubed. Now, if you take the inverse, which is g of x, the cubic root of x, the opposite happens. What was the range of f is now the domain of g. In other words, the input values. So when we input the values of the range of f, which is now the domain of g, when we input these values, the output would be the range of g, which before used to be the domain of f. So you get a flipped situation. Everything turns backwards, right? So in the next slide, you're going to see the graph here to the left in figure 2.21, the graph of x cubed. So what is interesting about x cubed? Well, x cubed is what is called a one-to-one function. That means that for each x value of the domain, there will be only and only one y value. We said that if you grab some values from the domain of f of x equals x cubed, and the examples we had were 3, 2, 1, I think we also had negative 1, negative 2, and negative 3, and these would map into the domain, or the range, excuse me. So the domain would be the x value, so this would be the domain, and this would be the range, right? So each and every value for x in the domain would map to one unique value in the range for y. So remember that 3 would give us 27, and then 2 would give us 8, 1 would give us 1, negative 1 would give us negative 1, this would give us negative 8, and finally negative 27. So this is a classical case of a one-to-one function. Now, the inverse of this was, of course, the cubic root of x. And that would also be a one-to-one function. So what is an easy way to determine whether a function is a one-to-one function by looking at its graph? You can draw horizontal lines. So this is what's called a horizontal line test. And notice that when you draw horizontal lines, you can only go through the graph once. You might think that at this point you can go through the graph more than once, But in reality, if you zoom into these graphs, it's going to look more like this, like a curve that comes here and then just bends up and goes up. So it really doesn't go through the graph more than once at y and x equals 0 or the origin. So this is a one-to-one function. Now, the interesting thing about inverse functions is that they are a mirror image of each other across the so-called identity function, which is this line, y equals x. So this line here, this green line, is y equals x, and it's a line that goes through the origin at an angle of 45 degrees. And when you have a function f and its inverse, they are symmetrical about the line y equals x. Now, f to the minus 1 is another way of saying inverse of f. So keep that in mind as well. So next we're going to talk about the existence of an inverse function. So to the left we have figure 1.22 with a function f of x equals x squared, a parabola. So does this have an inverse? Well, no, right? Because if you do the horizontal line test, notice that you're going to have two different x values, for example, two different x values that map into 10 and so forth. There's many, right? Because it crosses the graph. Each horizontal line crosses the graph twice. Therefore, this function does not have an inverse because it is not a one-to-one. It is a many-to-one. This is what's called a many-to-one function. So a trick you can do in order to find the inverse of a function like this one is limit the domain. So notice that in figure 1.23 we have g of x equals x squared, but the domain is limited to values of x that are greater than or equal to 0. That's why the graph starts at 0 and just goes towards the right, in terms of x. In terms of y, it keeps going up, obviously, because as you square larger and larger numbers, the line would go up. Now, you can also do the opposite, meaning that you can also limit the domain to x values that are less than or equal to 0 for another function. Let's say h of x equals x squared, as you can see in figure 1.24. So this one would be the same half of the parabola, but this time you're going left and always up, right? Because even if you square negative numbers, they're going to go up. The fact that negative numbers become positive when you square them is the reason why this is a many-to-one function. Okay, so here we are with example 2.15, and it says, consider the function g of x is equal to x over x plus 4 with the domain of f such that x is such that x belongs to R, but x cannot equal negative 4. So x is any real number except negative 4. That's the domain. The function that is the inverse of g is g to the minus 1. Now this is not the same. G to the minus 1 is not the same as 1 over g as we learned from doing the power rules, right? So this is false as far as the notation for functions. The inverse is not 1 over g, just so you don't confuse that ever. And notice that if you look at the two functions, it doesn't work that way, right? It's not simply flipping this up and bringing this down. No, it's a different operation where you have to exchange x and y and then rearrange. In any case, we don't have to do that. Now, they give us the inverse, so this is the inverse. Part A, use a GDC, graphing display calculator, to confirm that the domain and range of GR, we already know what the domain is, which is any real number, except negative 4. And the range, they say, is any y value such that y belongs to the reals, but y does not equal 1. So that means all real numbers except 1. So now let's take a look at the graphing display calculator and let's confirm the domain and range. Okay, so here we have the graphing display calculator and we're plugging in the function. So notice that it's x over x plus 4. Remember that you have to use parentheses, otherwise the calculator will not understand what you're trying to input there, right? Okay, So then all you do is hit the graph button, and there is the graph. So let's look at the domain. So we said before that the domain of a function is the input values, or x. So what happens in terms of x? So notice that we have x values that give something, and then all of a sudden the function shoots up, right? It goes up. Now if we draw a dotted line that goes through this point here, what point is this on the x-axis? Well, if we count, it's -1, -2, -3. This is -4, -4. All right, so notice that then after we go through -4, which the function doesn't touch at all, it does not touch the value x equals -4, and then it continues into infinity as far as x is concerned. So the function is, remember, x over x plus 4. And the domain is x such that x is real. And as we can see in the graph, the exception is that x cannot equal -4. You might ask, but why? Well, very simple. The solution is right here. This is the reason why. What happens if you plug in -4 here? Well, you would get 0. And remember that you cannot divide by 0. Anything divided by 0 becomes undefined. So at -4, at x equals -4, it becomes undefined. That is the domain. Now, how about the range? So the range is going to be the output or the y values, right? The y values. So we have to look at the graph in terms of y. So we have to go from, before we went from left to right, now we have to go from bottom to top. So notice that we go up, we go up, we go up, and then all of a sudden this thing turns right and then just splits. I mean, it goes here into infinity, but what happens to it? So what value is this? Notice that if we draw a dotted line here, a horizontal dotted line, the graph does not touch y at that value. And what value of y is that? Well, this is 1. This is the value 1. Okay, so we go up, the graph gets interrupted. Then if you go through 1, it continues into infinity, right? Above 1, with reference to y, it goes up into infinity. So that means that y is such that y is real, but y is not equal to 1. But why so? Well, that is because if you plug in very large numbers here, very large numbers, huge numbers, think of a number like 1 billion. So if you divide 1 billion by 1 billion plus 4, this is going to be approximately 1. It doesn't matter if it's -1 billion, right? Because if you do -1 billion over -1 billion plus 4, that's still going to be very close to 1. And the bigger that number, the bigger the number here, right? We're talking about billions, but let's talk about trillions. Talk about trillions, this 4 becomes insignificant almost. So what that tells us is that the graph of this function, as x increases into infinity or decreases into negative infinity, the graph itself, the y value, will get closer and closer to 1, but never quite reaching 1. It will never reach 1 because this 4 here, this plus 4, is always going to affect the fact of it reaching 1. So it's always going to be close to 1, but not quite 1. Okay, so this helps us respond part B, as we're going to see soon. So for part B, they want us to write down the asymptotes. It says here, write down the equations of all asymptotes for the graph of G. So let's go back to the graphing display calculator. So just a while ago, we drew a vertical line that went through x equals -4. So this line is x equals -4. And then a horizontal line that went through y equals 1. Well, those lines that the graph will never touch is something called asymptotes. So this is what's called a horizontal asymptote. And then this one, because it's in terms of x and it goes up or down, it's going to be a vertical asymptote. Okay, so now for part C, they want us to write down the domain and range of the inverse of G. The inverse of G. So look, if we have G, right, or G of x, and these are the x values, whatever they are, the x values. Remember that this is known as the domain. And then as we input these values into G of x, we're going to get y values that are the range. And then if we have the inverse down here, the inverse of G, then the range of G becomes the domain. This will become the domain of the inverse of G. And these x values that we had here are going to become the range of the inverse. So that means that we already have the domain and range of the inverse, because this is going to be the domain. But of course, because it's a domain, it has to be in terms of x. So the domain, let's say the domain is going to be x, such that x is real and x cannot equal 1. And you can see this here, right? X cannot equal 1, because if x equals 1, this would be 0 and it would become undefined. Then the range is going to be the domain of G of x, but in terms of y. So the range here is going to be y such that y is real, but y cannot equal -4. So for part D, they want us to find the following. It says the graphs of G and its inverse intersect at the origin 0, 0 and at point A. Use a graphing display calculator to find the coordinates of A. So we're going to graph both G of x and its inverse, and we are going to find out what the coordinates of A are. So notice that here we have both the functions, right? The top one would be G of x, and the bottom would be the inverse of G of x. Now notice that both denominators are in parentheses, otherwise the calculator will not interpret the information correctly. So once you have plugged them in, click on graph, and there you go. So remember that they said that they intersect at 0, 0. So that's right here. So the blue graph, as you recall, is G of x, and the red graph would be the inverse of G of x. So now they're asking us to find this point of intersection right here, right? That point of intersection. So how can we find that? Well, it's very simple. What you do is that you use the graphing display calculator as follows. You hit second function, and on top of trace, you're going to see calculate and option 5 intersect. So click on that, and then it's going to ask first curve. So move a little bit up from the intersection, or to the right in this case, a little bit to the right from the intersection. And yes, so the red curve is the first curve. That's fine. Let's just click on yes or enter. And then it's going to ask for the second curve. Here you have to be careful because you have to go below the other value, otherwise it's not going to find it. So you have to go below. Oh, that's not the right curve. It's the other curve. There. Okay, so once you are below what you estimate to be that intersection, you click on enter again. And finally, it's going to ask for if you approve of a guess, because that's what it actually does. It's going to guess the value by testing a lot of values between those 2 points. So hit on guess, and there it is. So the intersection is -3, -3. We could have estimated that by looking at the graph. But of course, it's a little more exact with the GDC technology. So this is -3, comma, -3. Okay, so here we are finally on part E of example 2.15. And it says, write down the equation of the line that passes through points 0, 0 and A. So before we said that A is -3, comma, -3. Let's recall that an equation of a line can be found by using the point slope formula, which is y minus y1 is equal to m times x minus x1, where x1 comma y1 is a point and m is a slope. So let's find the slope first. Slope is equal to difference in y over difference in x, or rise over run. So for y it would be -3 minus 0, and for x it would also be -3 minus 0, and this is obviously -3 over -3, which is equal to 1. Okay, so what do we have here? We have, let's use the coordinate 0, 0, because it's the easiest one, right? So we would have that y minus 0, that's just going to be y, is equal to 1 times x minus 0. So notice that this is going to be y equals x. So y equals x is the identity function. So let's look at the graph and see something very interesting here. So here I am back with the GDC, and notice that I have plugged in g of x, the inverse of g of x, and y equals x, or the identity function. So if you click on graph, there you go. Notice that this line, the line that we found, we said this was y equals x. This is the identity function, and it goes through the points, right? 0, 0, and -3, -3. But there's something else that is interesting, because this is g of x, the blue line we said was g of x, and the red line, or the red graph I should say, is the inverse of g of x. Well, notice that they are symmetrical with respect to this line y equals x. So there's a mirror image. For example, if you take this part, it's mirrored here. If you take this part, it's mirrored here. This and this are the mirror of each other, and this part and this part as well. So that means that the identity function lets us know if two functions are the inverse of each other.